Let's talk about thermodynamics. And I know what you might be thinking. Dusty old textbooks, right? Complicated equations. But let's just forget all that. I want you to think of thermodynamics as the fundamental rulebook for how energy works in our entire universe. Seriously, it governs everything from your morning coffee getting cold to how the stars shine. And it all kicks off with a really simple question, one you've probably asked yourself without even knowing you were doing physics. So think about this. Why does a hot cup of coffee always cool down? But you've never, ever seen a lukewarm cup on your desk just spontaneously start boiling. It seems obvious, but the reason why gets to the heart of some of the most profound laws in all of science. Okay, so before we can understand the rules of this game, we have to know who the players are. And in the world of thermodynamics, the key pieces on the board are energy, heat, and work. We've got to meet them first. You know, for a long time, scientists had a totally different idea about what heat was. They imagined it was this invisible substance, this caloric fluid, that would literally flow from hot things to cold things. But we now know that's not right at all. Heat isn't a substance, it's just energy on the move, energy in transit, going from one place to another because there's a difference in temperature. The big aha moment came from an experiment back in 1798 by a guy named Count Rumford. He was boring out cannons, and he noticed it generated a ton of heat, like enough to boil water. But the crucial observation he made was that the amount of heat had everything to do with the work being done by the horses turning the drill and almost nothing to do with how sharp the drill was. This was a game changer. It showed that mechanical work could be turned directly into heat, which totally shattered that old caloric fluid idea.
So, let's get to our first rule. And funny enough, it's called the Zeroth Law. It actually came along after the first and second laws, but it's so fundamental that they had to stick it at the beginning. This is the rule that basically sets up the game board, because it's the one that gives us the whole concept of temperature.
And the Zeroth Law is built on this idea of thermal equilibrium. It sounds a little technical, but the concept is super simple. It just means when you put two things in contact and their properties, like their temperature, stop changing, they've reached a balance. They're in equilibrium. This simple but pretty profound idea is actually why thermometers work at all. Okay, so think of the thermometer as system C. If you use it to measure your coffee, which is system A, and then you use it to measure a bowl of soup, system B, and they both read 60 degrees Celsius, well, then you know without ever having to put the coffee and the soup next to each other that they're at the same temperature. They're in thermal equilibrium. That's it. That's the Zeroth Law in action. All right, now for the famous first law of thermodynamics. And I like to call this rule simply, you can't win. This is the universe's law of conservation of energy. It sets a really strict, unbreakable budget for every energy transaction that happens. So, the law is captured in this neat little equation. Now, don't worry about the symbols, the concept is what matters. And it's pretty simple. It just says that if you add heat to a system, that's the Q, like say the steam inside a piston, that energy has to go somewhere. It can either increase the internal energy of the steam itself, making its molecules jiggle around faster, that's the U, or it can be used by the system to do work, like pushing the piston up, and that's the W. None of that energy is ever lost, and none of it is ever magically created out of thin air. Think of it like this. The universe has a fixed amount of energy. That's it. You can move it around, you can change its form from heat into work, you can store it, but you can never, ever create more energy than you started with. This is the law that tells us that those perpetual motion machines people dream about are just impossible. You just can't win the energy game by getting something for nothing. And this brings us to the most profound and maybe the most misunderstood rule of all, the second law. Because if the first law says you can't win, the second law delivers even tougher news. You can't even break even. So here's the thing. The first law by itself doesn't actually forbid a lot of weird stuff. It wouldn't forbid that coffee cup from getting hotter by sucking heat out of the cool air around it. Energy would be conserved, so the first law would be fine with it. It also wouldn't forbid a book on a table from gathering up all the random heat energy from the table's molecules and using it to launch itself into the air. But we never ever see these things happen, right? There has to be another rule, a rule that gives a direction to reality. And that rule is the second law. One of its formal statements is this one, from Kelvin and Planck. Okay, I know that is a mouthful. So let's just break down what they were really getting at. In much simpler terms, it means the universe has a one-way street for energy. What it really means is that energy naturally wants to spread out. It flows from being concentrated to being dispersed, from orderly to disorderly. In any real-world process, whether it's your car engine or your own body, you can't convert 100% of heat energy into useful work. Some of it is always going to be lost as low-quality waste heat, and that waste heat increases the overall disorder, or as physicists call it, the entropy of the universe. And listen, this isn't just a problem with our current technology. Scientists imagined a totally perfect frictionless engine, what we call a Carnot engine. It's the most efficient engine that physics could possibly allow. And even this ideal engine, this perfect machine, still can't break the rule. As long as you're taking heat from a hot place to do work, some of that heat is inevitably going to be dumped into a cold place. It is fundamentally impossible to be 100% efficient. So let's put it all together. The first law, that's the baseline. That's the absolute budget for energy in the entire universe. In the game of thermodynamics, this rule tells you one simple, unshakable truth. You can't win. And then, just when you think you've got it, the second law adds the real killer twist. Not only can you not get more energy out than you put in, but you can't even get all of that energy back as useful work. There's always a tax you have to pay to the universe. You can't even break even. Okay, so those are the rules of the game. Let's just step back for a second and think about what they mean for us and for the universe as a whole. So, here's the ultimate takeaway, the summary of the whole thing. The Zeroth Law gives us a way to measure hot and cold. The first law tells us energy is conserved. The books always have to balance. And the second law? Well, the second law gives time its arrow, telling us that the overall trend of the entire universe is always towards more disorder, more entropy. And this isn't just some abstract physics concept. These three simple rules explain our everyday reality. They explain why your coffee gets cold. They explain why you can break an egg, but you can't unbreak it. And they explain the fundamental limits of every piece of technology we will ever build. They really are the rules of the game. And all of that leaves us with one final, pretty cosmic thought to chew on. If the second law says that the total disorder of the universe must always increase, that every single process pushes it just a little bit closer to a state of uniform, lukewarm equilibrium,